Good morning.
How'd you go with homework?
I don't think I quite get it yet.
You don't get it?
Yeah.
Well, so we're doing a recap today. That'll help us with the assignment. I struggled with question 2 a lot, but question 1 was okay. Because the mail gets you.
Not sure.
Yeah. And how's your weekend?
It was good. It was good. It was kind of busy.
Yeah?
Yeah, I had family over and the cousins over, so it was quite hectic. But it was good. Yeah. And you? How was your weekend?
Yeah, it was good. It was good. I did some cooking for my mom. We like to bake together.
Oh.
So yeah, just made some chocolate cake.
Good morning, students.
Morning, ma'am.
How are you? What's so much noise about? I could hear you guys speaking from the office. Okay, and giggling as well. I guess the boys were loud. They were giggling. And what's up at the moment?
Just talking about our weekend.
The weekend.
Yeah.
Yes, I'm pretty sure the weekend must have been interesting. And it's Monday morning, first day of the class, first period. Must have been tiring as well, right? But we'll need a lot of energy today. We're discussing recapping and going back to Coulomb's law. And today we'll be learning how to apply Coulomb's law, right? Boys at the back, are you clear on that? I think the boys are still sleeping. Okay, so before we start off, since you guys are making a lot of noise, I have a task for you. So what shape can you see in that?
A circle.
Right. So find out, where does that circle end? Not really a punishment for your noise, but something to keep you thinking, right? And this you'll get it in the next class. Where does the circle start and where does the circle end? Kaylin, you started to figure out already? Okay, so that's your fun activity, fun assignment. And you need to come back with an answer whether where does the circle start and where does the circle end. Great? Perfect. Now let's recap from our previous class. What did we do in our previous class, students?
We learned about Coulomb's law.
Okay, and would you like to explain more about Coulomb's law?
We were both saying we're struggling with the homework, so we're really excited for the recap today because I'm just a bit lost.
Okay, no worries. So the homework was to actually define static and also go over and find fields that use Coulomb's law as an application, right? So once we will go over it again, little by little, you'll get used to it. And this is not a new concept, that's for sure. Right? I can understand you two are international students who are studying with us this year. So our curriculum is different from your curriculum. And definitely, Michelle and them should help you out to follow up with this. Great? So we'll try to go over again, we'll try to recap, and we'll try to go and visit the Coulomb's law's history. Very important thing, I know this is not a history class, but it's very important to know why someone discovered this particular idea. Why was this discovered? What is the purpose of it, right? Did someone really want to know what is Coulomb's law, or was it just the apple that triggered Newton, or was it something else? So we'll try to find out that as well. Great? Okay, so recapping part, yes, like I said, Coulomb's law. Let's revisit Coulomb's law from last class. In last class, we talked about the principle of Coulomb's law. And I'm pretty sure Michelle can answer that question as well. So, when we talk about Coulomb's law, we talk about charges. And most of you are chemistry students as well. So, you're well aware of charges, right? And these charges have certain amount of forces in them, right? Do you hear that term, like charges attract, like charges repel and unlike charges attract? Yeah. Not in other terms, in terms of physics. Yes, that's actually what we're trying to apply over here. That is how we get Coulomb's law into action, electrostatics into action. Now, last time I taught you a method to understand simply what the topic says. So, break the terms apart, right? We learned about electro and we learned about statics separately. So, electrostatics is the topic. And if you break it apart, you get electro and you get statics. Electro means electricity. The word electricity comes from electron. And when we talk about electricity, charges comes in, right? And when we talk about statics, we have two terms, kinematics, statics. Static means it's stationary. So how are we going to get charges to actually generate electricity when they're at stationary position? We're trying to study charges in their stationary position. That means when they're not actually moving. And what causes them to move towards each other or away from each other. Perfect? Okay, let's jump into today's lesson then. The main outcome, the main objective for today's lesson, it's also in your textbooks as well if you read through, is to get you guys going and understanding the application of Coulomb's law. So the main purpose for today's class is for you to understand how to solve practical explanations of it, how to actually calculate the force between this particular charges using Coulomb's law. That is the formula itself. Okay, let's go into a brief history of it, shouldn't we? Sorry about it, we don't have a projector in our school, Kaylin and Hazel. Our school is a bit old and still following that modern, traditional time of learning, not into modern time as well. We have certain issues with ICT and PowerPoint projection. You may ask the other students as well, but you can always have a look through my laptop. Guys, come closer, please. The boys at the back, come closer.
When I looked into the history of Charles Coulomb and his equation,
a lot of interesting things
that he was one of the
about
most influential engineers of the 1700s. And his accomplishments are even more impressive when you consider that his background was decent, but not considered good enough for the status-focused people in charge. Even worse, his father lost the family fortune, he had a boss that almost killed him, and he lived in one of the more turbulent times in history. Ready for the story? Let's go! Electricity, 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 electricity. Before I start the story of Charles Coulomb, I have to warn you that I could only find 2 portraits of the man, so I kind of overused them. Anyway, Charles Augustin Coulomb was born in the south of France in 1736 to a middle-class aristocratic family. His father was government administrator. When he was around 10 years old, his father got a job in Paris, and Coulomb started attending the local school. However, his lineage wasn't good enough to be a full-time student. You needed 4 generations of noblesse. So instead, he became what was called a martinet, or audit of the class. When he was a bit older, he entered the College Royal, where he was mistreated a bit for his background. But he had a fantastic math teacher and fell in love with mathematics. His mother was distraught as she wanted him to be a doctor. But his father, who is described by contemporaries as a good-natured and unsuspecting fellow, didn't seem to care, but also seemed to have a lack of mathematical skills himself, as his father then lost all the family money in the stock market. Legitimately frustrated, Coulomb's mother, Catherine, kicked Coulomb's father, Henry, out of the house, and Henry went back to his hometown of Montpellier. Coulomb's mother, who still had some money left that she had inherited, tried to blackmail Charles into becoming a doctor, but he rebelled and left Paris and went to live with his father in Montpellier. He didn't have very many options. He could join the priesthood, or he could join the military as an engineer. Coulomb decided on the military and joined a military academy in 1760 when he was 24 years old. At that school, he took classes in experimental physics from the scientist Abbé Nollet, who was considered France's leading electrician. Anyway, after about a year of instruction, Coulomb became a lieutenant in the military engineering corps. And after spending 2 years doing geological mapping, he was transferred to the island of Martinique. 28-year-old Coulomb ended up being a lead engineer designing Fort Bourbon, a 6 million livre project with 600 workers. Coulomb was a superb engineer and ended up being promoted to captain after only 6 years of work. Unfortunately, he also got very ill with a tropical disease and asked his superior, named Leboeuf, to let him be transferred back to France for his own health. Leboeuf agreed, and in 1770 wrote to Versailles asking for Coulomb to be transferred home for his, quote, future value to the state. Then 5 days later, Leboeuf had a change of heart and realized that this would be a good way for Leboeuf to get home. So he wrote another letter to Versailles saying that he, Leboeuf, was ill and needed to come home. But it was okay, as Coulomb could take care of things, as Coulomb, quote, has been in charge of the work at Fort Bourbon since the beginning, and whom I have decided to keep here for the next year. Poor Coulomb took another 2 years to return to France. According to a biographer, Coulomb's health was so affected by his illness during an 8-year tour of duty in Martinique that he was never again a well man. Back in France, Coulomb wrote a paper about using calculus to determine building stability. The encyclopedia says that his paper of 1773 contains, quote, almost an embarrassment of riches, including a theory of soil mechanics that remains in use today in basic engineering practice. In 1777, the Paris Academy had a competition to design a very low-friction compass to detect.
Okay, so far, what did you understand about his history? He was an engineer.
He had a good maths teacher.
He had a good maths teacher. What else? He didn't come from a very promising background, did he? There were a lot of issues. Probably issues to also continue with his studies. What else?
Oh, he was ill.
He was ill. Who was also ill? Okay, there was a scientist known as Srinivasa Ramanujan. If you've heard about him, he was the man behind infinity. He was an Indian man behind infinity. And he also had tuberculosis. He was terminally ill and he died eventually because of it. So why do you think these scientists, these engineers in that late 1700s or 1800s who found these influential theories actually passed out because of their illnesses? What could be a reason why they got that illness?
Too much time studying.
Too much time studying, right? What else?
Not enough vitamin D.
Not enough vitamin D. Good. You're bringing in your biochemistry here. Yes, that could be a reason. That could be a very prominent reason to why they actually suffered and became ill. And there are so many scientists, like if you see the pictures of them. If you see Einstein, it really looks like, what's wrong with his hair? Doesn't it, Kat? Would you say that? What's wrong with his hair? Yeah. Why is that? Because he didn't get time to actually get his hair. Most of the time, they're always in the laboratory and doing their work. Right? Okay, let's see what happens next.
Magnetic disturbances during the day, as the traditional magnet on a pivot had too much friction to record the variations that they were looking for. Coulomb worked on it for over a year and won the prize for a magnet held up by a thin silk string. This inspired him to start working on the physics of friction, which he published in 1781. An author of a book about friction wrote in 1956 that, quote, Coulomb's contribution to the science of friction were exceptionally great. Without exaggeration, one can say that he created this science.
So who created which science?
The science of friction.
Okay. And who was that?
Was Coulomb.
Okay. And what is friction? Good.
Coulomb and his magnet. The Paris Academy was impressed and installed a version in their observatory. But unfortunately, it turned out to be too sensitive. As an historian wrote, the compass twitched when the assistant sneezed, or when the door opened, and trembled when carriages passed the street. Coulomb attempted to isolate the needle in a chamber free from any drafts, but it would still often move when the assistant touched the outside. Coulomb eventually figured out that the person walking to the compass would often gain a little bit of electric charge, which would then make the needle sway electrically, not magnetically. Eventually, they grounded the needle and the outside of the person, and it seemed to solve the problem.
We'll come to magnetic forces later on. So remember this
the twisting force to study the electrostatic force. See, the problem with studying static electricity is that usually the forces are so slight that you can only see movements of little pieces of fluff or feather or wealthy gold foil. Most scales cannot measure such minute forces. Coulomb decided to study the force of twisting, called the torsional force. He wondered if twisting items worked in a similar manner to springs in what is called Hooke's law. Robert Hooke was a scientist who lived 100 years before Coulomb in the time of Newton. Fun fact, Hooke claimed that he had proved that the force of gravity depends on 1 over the distance squared before Newton did, but he didn't want to share it, claiming he would, quote, conceal it for some time, that others might know how to value it. Hence, Hooke never revealed it. Some laws Hooke did reveal and understand were about springs. First, Hooke found that for moderate disturbances, the amount springs compress or stretches is direct proportion to the force on the spring. So if you double the force, you double the amount the spring stretches. And how much a spring stretches with a given force depends on the strength of the spring, called the spring constant. Therefore, if you know the spring constant...
So do you remember this? Hooke's law? Spring constant? We have learned that in simple harmonic motions. When we looked at the motion of electricity, springs, and how energy can be transferred. So mostly you'll see in physics, we're talking about how one particular medium can transfer energy to the other medium, right? Whether it be in terms of springs, whether it be in terms of charges or physical bodies. Very important for you to understand that essence of physics, to completely understand physics.
Constant, and you know the amount the spring is displaced, then you can know the force on the spring. This is how most simple spring scales work in like a grocery store today. Hooke also determined that if you pull a spring and let it go, it will oscillate up and down at a steady rate until it stops. Therefore, the frequency of the spring's vibration is solely due to the mass on the spring and the spring.
So we'll stop there because it's more of Hooke's law now. But let's recap from what you have learned through the video. What actually triggered Coulomb to go and study about electrostatics?
Friction.
Friction? Are you okay?
His compass.
His compass. So he's discovering, right? And what he actually found out towards the end?
That the person moving towards the compass would gain a negative electric charge.
Okay.
And that would trigger it and we create electrostatic force instead of magnetic.
Right, very good, Kaylin. Good. And Hazy, you're okay?
Yeah, and also like the twisting the needle, it's like torsional force. Yeah.
Okay, how about Sarah and Michelle at the back? Are you guys okay with that? Yeah? Okay, good. Now let's jump into the main part of today's class, the calculation part. Let's recap, or let's just have a look at this question, right? This example. I'll solve this example for you people, and then later on, we'll try and do this class assignment together. Discuss amongst groups so that you can actually come with a proper answer. Even if you don't get a right answer, it's okay. We are here to make mistakes and learn from our mistakes. I remember when I was in university, I had this very good colleague, and he used to say always, make as many mistakes as you can. Because the more mistakes you make, the more you learn from it. Don't make mistakes that will be costly in your exam, right? Okay, so let's have a look. There are two charges, if you can see that. And again, remember the formula. What does the formula say? Fe is the electrostatic force. Very good, Hazel. Electrostatic force. And we have a expression given. So the expression again is the Coulomb's law, mathematically expressed. It states that the product of the two charges. So the two charges, you'll see a value associated with that, right? Mm-hmm. These are the value of the electrical charge. The electrical charge, and then R squared. What is R squared? It's basically the distance between it. So whatever the distance is, you take that and square that. Okay? Let's try. Before that, okay, it is fine. We understand where the Q comes from. We understand where the R squared comes from. What does K represent? We learned this in the last class as well.
Is it a constant?
Yes, very good. K is a constant. A Coulomb's constant. And in the last class, we were talking about how to rewrite the Coulomb's constant. Now let's try to rewrite Coulomb's constant in terms of other expressions, right? Let's replace K with something else. Now the value of K is generally 8.99 times 10 to the power 9. But if we are to replace this particular value you can rewrite K in terms of 1 over 4 pi epsilon naught. So this is another way you can express Coulomb's law. How? I don't know. You will get Fe is equal to 1 over 4 pi epsilon naught into Q1 Q2 over R squared. So you can rewrite Coulomb's law in terms of this. Why I'm trying to teach you more about epsilon naught and what does epsilon naught mean is basically permittivity of space. It is also a constant. And sometimes we get confused whether the K value is given or not in the paper. You'll see there are so many K values that will be used. Like F is equals to Kx, Hooke's law. So if you get confused between the K values, the two constants, you can always replace it and write it in terms of epsilon naught. There's just one value for epsilon naught. Okay? We'll go over that epsilon naught when we have an actual look of our final paper. And in that paper, we'll go over the constants list as well. There's a list of constants that has been provided, and it's important for you to identify the constants properly so that you don't make mistakes in the exam. Okay, that makes sense. Now, let's try and do this calculation. Would you help me out? Come on. What is the value of K that I'm going to take?
1 over 4 pi.
Would you like me to take this or take this?
Maybe 8.9.
Okay, let's take 8.99 times 10 to the power 9. What else? Okay, first charge. What does the E stand for and what does the P stand for?
Is P for positive?
Okay, and what is positive?
Plus charge.
And what do we call that plus charge? Chemistry, come on, responses?
Cation.
Cation? Have you heard about protons and electrons? So this is generally a proton. It has a protonic charge. And this is an electron. And like you have said, Kelly, it's right. This is a positive charge and this is a negative charge. And this is the basic of any nucleus if we talk about an atom. Right? In your chemistry class, you must have learned about atoms. And that's where this protons and electron comes in. So you'll see all the sizes are interconnected. Few things you learn in chemistry will come back to physics. Okay. So I'll take the positive charge first. 1.6 times 10 to the power negative 19. How about this? How will I take this? It's a negative charge. So should I include the negative sign or should I not? The answer is itself in the question. 2 minutes, think about it.
It doesn't say negative Q2, so would you exclude the negative?
Okay, we'll exclude the negative. It's a good answer. How about I say, bring your maths knowledge over there. There is a sign that you can see. Is this a normal bracket? No. It's an absolute bracket. And what's the rule for absolute?
We ignore the charges.
We ignore the signs. Whatever is going to be negative inside the absolute sign will become positive if you remove the absolute sign. So that means we're just taking the positive value. Okay, let's take the positive value then. Now, explain me one thing. We have taken the positive values. What is the purpose of that negative and positive there? Then why is it that if we have just taken a positive answer, a positive value?
Is it to determine like charge?
Very good, very good. It is used to determine the final force, whether it will be attractive or whether it will be repulsive. Very good. Okay, what is our R?
4.3 times 10 to the negative 11.
Okay, would I just leave it like that? Or would I take a squared value of it?
Square.
Okay, you want to do it for me? Use your calculators and get the answer for me. Be careful of negatives and the powers. You're okay? Good. Yes, Karen, go ahead.
I got
Do you want to write it? Okay, we have the same thing?
yeah, same.
Great. And what should be the unit? What do you think is the unit? FE. What is the unit?
Newton.
Very good. It's Newton. Why is it Newton?
It's a force.
Very good. Very good, Hazel. That's excellent. Yes, it's a force. So we'll get Newton. Not coulombs. Coulombs is for the charges. Okay, at the end, we're trying to find a force. Now, what type of force can you experience over there? Attractive or repulsive?
It's attractive.
Okay. Would you like to write it for me? Think about it and then write. She's saying it's attractive. The boys in the back are saying repulsive. Some of them are screaming repulsive. What do you think? Attractive or repulsive? And maybe you can explain why do you think that? Yeah. And why so?
I think it's attractive because we have two, what do you call, unlike charges, you have negative and positive, so they're going to attract. Unlike they're the same. Right.
Very good. Clap for her. You did a great attempt on that. Very good. So that's a basic simple example. Now let's say if my r squared value is greater, then what will happen to FE?
It will get smaller.
Very good. And that is what? What type of relationship? There's two. Direct and one is inverse. Inverse. Right. So that's what it states, right? The force is directly proportional to this product of the two charges and inversely proportional to the square distance. Remember that definition and remember this equation. A similar representation of gravitational law is there. Just instead of Q's, you will have M. Because when we talk about gravity, we talk about masses. Okay. Now, try with this assignment. Try to do this assignment. It's a very simple assignment, however, there is no diagrams given. So I would like you to actually diagrammatically show what this particular scenario is like. What's happening. To make it more easier to enhance your understanding. Write down the question, try to do it. I didn't give you worksheets because I'm pretty sure you'll lose the worksheets by the end of the year.
Yes. No, it's okay. I figured it out.
You figured it out? So this is a basic question that you can expect in your exam. The exam that we will have after 2 weeks, your short test. Remember, I could pick up any of the question and place it there on electrostatics. And also, we will look into superposition in our next class. Now, you'll learn about superposition in terms of Coulomb's law as well, where we'll see how to find the forces when there is a triangle involved. So, at the moment, the charges are in linear position, right? They're moving straight. What about if the charges are placed like this? There's one charge over here, one charge over here, and one charge over here. That is where we'll use superposition in our next class. Okay, how was your field trip on Friday to USP Open Day? Did you get to learn about a lot of things? As a form teacher, I was there with you, but I was also part of the careers team for the other career students. So mostly I was divided into both parts. And I didn't get to visit the booths that you people went to visit, students. I guess you did go and have a tour around the science block. You did see about physics and all.
Hazel, did you get this?
Oh, I'm yet to finish that.
I liked the chemistry block the most.
Okay, what was so interesting about chemistry?
They had lots of exhibits on special topics. So they were looking at like essential oils, and they were also looking at environmental chemistry, and they were looking at polymers, which is really interesting. So lots of real world applications in chemistry, which I really like.
Great. That's good to see you enjoy. You get to learn a lot of things when you go for open day. And next year you'll have to definitely choose a field. So have you decided where you will go?
Probably into chemistry.
Chemistry. And would you choose USP or?
Yeah, I would choose USP.
Okay, that's great. Hazel, what's your plan?
I'm thinking of going to physics, yeah.
You want to go to physics? Okay. There was this very interesting experiment in physics, which I came across when I went to the physics department. They had a beaker, right? Beaker full of oil. And then there were two other beakers inside it, but we couldn't see the beaker. The two beakers that was actually inside the oil. It disappeared. So everyone was thinking, where is that beaker? Like, first, because the oil, if it contains some impurities, you would be able to see lines of the beaker inside it. But we didn't know that there were actually... Are you okay?
I'm sorry, yeah.
There were two beakers inside it. So that is an application of Snell's law, one of the principles, that says that we talk about in terms of light, diffraction, refractive index of light. In terms of refractive index more. So in oil, you can see the bending of light, and because of that, it becomes translucent. You can't see anything inside it. If it was transparent, you could see everything inside it. Interesting, right? Maybe you could try it at home. Take a glass of oil or take a glass of water and try it in both. See whether it disappears in water or not, or whether it disappears in oil or not. Okay? Got the answer?
I don't think so.
Okay,
I got 2.16 times 10 to the negative 23 neutrons.
Okay, and how about you?
I got 2.16 times 10 to the power of 8.
What happened there?
It was the calculator.
It's always the calculator. Okay. It's almost time. So take it as your homework and do it. Discuss it in your group, and then we'll go over it again. And be careful with the calculator. I'm pretty sure you'll get the answer there. But you're close. You guys are close. Don't worry. Okay. Thank you for the class today, students, and I hope you have learned how to apply Coulomb's law. And yes, remember, next class we'll be going over superposition principle. That means we'll be looking into 3 dimensions. How can we actually find Coulomb's law, using Coulomb's law, the force between charges which are located in terms of a triangle. It's a right angle triangle. And find out where does the circle start and where does the circle ends. Thank you for coming, and you may now wait for your next teacher. I think it's Max, is it? Yeah.
Thank you, ma'am.
Thank you. Have a nice day, students.
You too. Bye.
Bye.